Hello and welcome. This is our case 4 of electric flux through a cube using the solid angle. So in this case, I have taken a charge. Now the charge is at the edge center of the cube. So this is our cube and the charge is placed at the edge center HE here, right? Now first of all, let's use the usual method that we do, that is flux through the cube. First of all, we'll see the charge is contained by the two faces. One is this HAE, this H, this DAEH, and then it is GFEH. So these two faces contain the charge. So flux through these two faces will be zero because the field lines will be parallel to the plane of the two faces. Now there remains only four faces, so all the flux will go through these four faces. So that means the flux through this face ADHE is equal to flux through FGHE is equal to 0 because they contain the charge. Now total flux is equal to charge enclosed divided by epsilon naught. Now what is charge enclosed by this cube? When the charge is at the edge center, we need 4 such cubes to enclose the charge completely. So contribution of the charge in each cube is only 1/4. That is q by 4. So therefore, total flux is equal to q divided by 4 epsilon naught. Now the question is the flux through each face equal to 1/4 of the total flux? Can we write flux is equal to total flux divided by the 4? No, we cannot write that because the four faces are not symmetric with respect to the charge, that they are not equally spaced with respect to the charge, right? So flux through each face is not equal to flux total divided by 4, which is equal q divided by 16 epsilon naught. Why? Because the four faces are not symmetric with respect to the charge. Now, if we look at the bottom face and the top face, this is bottom and top face, so they are equally spaced with respect to the charge, and then remains the other two faces, that is this GBFG, this CBFG, and then we have this face BCDA. So these two faces are symmetric with respect to the charge, but flux through these two faces is not equal to the flux through top and bottom. Now let's calculate what is the flux through these two faces, right? So for that case, I have to first calculate what is the solid angle subtended by the charge with respect to this face and then with respect to this face. I have taken this face separate. Now let me see first what is the solid angle subtended at a distance h from the one of the corner, that is at this point. Then we can calculate the solid angle subtended at this point. We know the solid angle subtended at point P is equal to sine inverse LB divided by under root of L square. Then it is plus H square, B square plus H square. So what is LB? L is here this and B is this and H is this much, right? So if this P shifts to Q, that means I take this point to Q. So I am reducing the H to H by 2, then omega Q, that is solid angle subtended at point Q, is sine inverse LB divided by L square plus H square by 4 times B square plus H square divided by 4, right? So that means solid angle subtended at this point by this face is equal to this much. For cube, now this L is equal to B is equal to H is equal to say. So solid angle subtended at this point is equal to sine inverse A square divided by 5 A square by 4. So that is sine inverse 4 by 5, right? But solid angle subtended at this point due to bottom and due to the top are same. So I can write solid angle subtended at Q is equal to this is equal to this. So that is sine inverse 4 by 5, right? Now, let's see what is the solid angle subtended by this phase, that is ABCD. This we have already calculated in the previous video, that is video number 3. So that is equal to sine inverse. Now it is here H by 2. So then it is L divided by under root of H square by 4 plus B square. Then it is L square plus B square. So that is 2 sine inverse. For cube, A square by 2 divided by A square by 4 plus A square plus A square. So after calculations, what we get, this is 2 sine inverse 1 by under root 10. So that is the solid angle subtended by BCGF. That is this BCGF. So solid angle subtended by ABCD is equal to solid angle subtended by BCGF, right? So now let's calculate what is the flux through these faces. So first of all, we'll see what is the solid angle subtended by this flux through ABFE. That is this ABFE, that is bottom face, that will be same as that of top face. So that is Q by epsilon naught, solid angle subtended by the phase divided by 4 pi. So that is Q by 4 epsilon naught sine inverse. This we have already calculated, 4 by 5. So it is 4 pi. Similarly, the flux through ABCD, that is this ABCD. So that is equal to Q by epsilon naught, solid angle subtended by ABCD divided by 4 pi. So that is Q divided by epsilon naught, solid angle subtended is 2 sine inverse 1 by root 10 divided by 4 pi, right? So the total flux through all these four faces will be the 2 times flux through ABFE, that is ABFE because that is also equal to through the top, plus 2 times ABCD, that is this ABCD, that is also equal to BCGF, right? So that is why I am writing here 2 times. So now doing a little bit calculation using these two values. So what we get, it is 2Q divided by 4 pi epsilon naught. Then it is sine inverse 4 by 5 plus 2 sine inverse 1 by root 10. So 2 and 2, so this will be Q divided by 2 epsilon naught. So now putting the values of these, that is 0.643 up to 3 places of decimal, and the value of this is 0.972, then divided by value of pi, that is 3.14. So it is Q by 2 epsilon naught times 0.5, which in fraction is 1 by 2. So this implies phi total is equal to Q divided by 4 pi epsilon naught. So that means the total flux through all these four faces is again equal Q divided by 4 pi epsilon naught that we have calculated. Now what is the fun of doing this? The answer to this simple question is, when we go through these types of problems, we stop here, we calculate the flux through the cube, that is total flux, but what is the flux through each face? So we are unable to solve that with the help of this method, but if we know the solid angle subtended by each face at the charge, we can calculate what is the flux through each face. That is what I have done here, and I have proved that it is equal to this value again.